In this video, we'll start learning about thermochemistry and look at energy. When we think about thermochemistry, we first have to think about thermodynamics. And thermodynamics is the study of energy and its transformations. When you look at thermochemistry, that's the study of the relationship between chemical and physical changes and the energy changes which involve heat. So thermodynamics is a study of energy and its transformations. In thermochemistry, we're looking at how that relates to our chemicals and how the energy changes, which usually involves heat. And when we first think about energy, energy is the ability to do work or transfer heat. Here in chemistry, we really care about the transfer heat part. In your physics class, you'll care more about the work. Right now, we care about heat. How is heat transferred? That's how we look at energy and energy transfers in chemistry. And so when we first think about this idea of work, energy used to cause an object to move is called work. So work equals force times the distance. And so when we think about heat and heat energy, that's used to cause a temperature change. So energy used to change the temperature of an object is called heat. And we use the symbol lowercase q for heat. And so heat always flows from a warmer object to a cooler object. Heat always goes from warmer to cooler. So the energy will go from the warmer object to the cooler object. And so when we look at kinetic and potential energy, kinetic energy is the energy of motion. This is the energy of movement. If we think about it in chemistry, our kinetic energy is the energy of our atoms moving, or the energy of our molecules moving. That's its kinetic energy. Potential energy is stored energy. So a potential energy in chemistry is the stored energy. So that's when we have our atoms locked into place. They have the potential to have more energy and move, but they're kind of locked into place. And so potential energy is always converted to kinetic energy. Objects can have both potential and kinetic energy at the same time. They can still have some potential energy, but also have kinetic energy. And so when we think about these, kinetic energy is the energy of our atoms kind of moving and jumping around. Potential energy is if we have them locked into place with their bonds, they have the potential to go from their locked in place position to moving around if I add more heat or more energy to it. And so you can think of a solid has a lot of potential energy because the atoms are locked in their defined locations. Gas has a lot of kinetic energy because gas atoms and gas particles are moving around. Something that has both potential and kinetic could be a liquid. In liquid, our atoms move, but they're still right next to each other. So they still have some defined locations and intermolecular forces. And so we can always convert between potential and kinetic energy. If we cool those molecules down, then they'll go from moving around a lot and they'll start slowing down. When they start slowing down, they start losing kinetic energy and start gaining potential energy. So when we're looking at these, kinetic energy, that's the relationship between mass and velocity of an object. In chemistry, we're often more concerned with the thermal energy or heat energy of the atoms or molecules. So we always look at the heat energy, and we always relate energy to heat and how hot something is in chemistry. That allows us to think about the kinetic energy, because atoms that are hotter move faster. And potential energy is the energy that the object possesses by virtue of its position or composition. So the most important form of potential energy in molecules is electrostatic potential energy. You can think of it as the energy of the atoms next to each other, so kind of their intermolecular forces gives us their potential energy. Because if they break those intermolecular forces, then they can start moving more. And so looking at our units of energy. When we're looking at our units of energy in chemistry, we really care about the joule, capital J. So that's the SI standard unit for energy, is a joule. 1 joule equals 1 kilogram times meter squared divided by second squared. Or we can just say a joule. An older non-SI unit that we still use a lot is called a calorie. And the calorie is defined by the heat required to raise 1 gram of water 1 degree Celsius. Or we can think 1 calorie equals 4.184 joules. Now, little calorie here, little kc, different than capital KC, capital C. Capital C is what we call a nutritional calorie. And the nutritional one, as you see, is what we write on the label of our nutritional facts. So on the label of any product that has a nutritional fact in it, or nutrition fact in it, the capital C there is a nutrition calorie, which equals 1,000 little calories. So our bottle of soda here contains 240 calories, 240 nutritional calories. Or you can think it contains 240,000 little calories. We can even go a step further and say that 240 calories, so our 240 calories equals 240,000 little calories. And if we want to convert to joules, that would give us 1 million joules of energy just in that one soda bottle. May think twice about drinking soda at this point. You're consuming 1 million joules of energy. So now that we know a little bit about our energy, we know a little bit about potential and kinetic energy, let's start looking at how we define these things. So we're going to look at definitions. When we talk about thermochemistry and the transfer of energies, what is it transferring from and what is it transferring to? So we have to start defining things. We define the system is the molecules we're looking at. So in my cylinder here, the system is just the molecules. And so we want that to usually reflect the reaction itself. And it, in our example here, contains just hydrogen and oxygen molecules is our system. The surroundings, everything else. Everything else in the universe can be considered surroundings. So here, the piston, the container, outside here, that's all surrounding. The system is just the molecules reacting, just the molecules themselves. Everything else, surroundings. And so when we have our molecules in there, let's say they're inside a liquid, I can still say the molecules themselves are part of the system. And then the liquid, if they're in water, that's the surrounding. So remember, it's whatever we define the system is the system. You get to define it. Everything else is considered surrounding. And so what happens is our system is part of the universe that's under investigation. And our surroundings is everything else. The state of the system describes its attributions. So that means if I want to talk about the state of the system, I can talk about its composition. It contains oxygens and hydrogens. I can talk about the temperature. We can say the system's at 200 degrees Celsius. Or I can talk about the pressure. Since it's a gas here, I can say the pressure is 2 atmospheres. All of that is letting me know more about the system. So when we talk about the state of it, that's letting me know more about the system itself. So now when we talk about a system, we have different types of systems. Our first one is an open system. And so that's one where matter and energy can be exchanged with the surroundings. So let's say you have your pot of water. We're going to make pasta. And it's on top of our stove. With our pot of water, we're heating it up. I'm adding energy into that system. The water molecules, they're going to start converting into a gas. And so I'll start getting some water molecules up here. I'm going to start exchanging matter and giving matter to the surroundings. And if you ever hold your hand above a pot of water when it's heating up, it starts to feel kind of warm. So you're also exchanging energy with the surroundings. Now, if you've ever heated a pot of water, you know it takes forever to heat if you have it open like that. It takes a really long time. So instead, let's say we have our same pot. It's my burner. It's my attempt at flames. And now I put a lid on my pot. If I put a lid on my pot, it heats up quicker. It starts to boil a lot quicker. And so what I've just done is I've created a closed system. That's one where energy is exchanged, but matter is not. So what we've done is we've created a closed system where we can add heat to it. If you put your hand above it, it's still kind of warm, but you can add heat to it. But now the water molecules, they can't leave the pot. They're stuck inside. So it's no longer exchanging matter with the surroundings. And then now if we have an isolated system, that's where energy and matter are not exchanged. So an isolated systems is one where neither energy nor matter can be exchanged with its surroundings. Isolated systems are kind of hard to create, but the closest one y'all can really think about is if you have your coffee thermos. So let's say you have your thermos. I'll call that a thermos. If you have a good quality one, your coffee stays hot for quite a while. And that's because on the lining of the thermos, it has a vacuum. So the vacuum creates a barrier where energy can't pass through. So that's how your coffee inside stays really warm versus just sitting in a regular coffee cup. Even if you put a lid on that coffee cup, your coffee still gets cold pretty quick. But in the thermos, it stays warm a lot longer. So our isolated system, if we had a perfect thermos, we can create a vacuum around the entire container and your coffee should stay hot all day. But since we usually have to have a lid or we want to actually drink the coffee somehow, there's a slight little break in the perfect seal here. So that's why it does start to cool off a little bit. It's not a completely isolated system, but it's not bad. It's pretty close. And so now that we know all about this, our energy is transferred to and from the surroundings and the system. And that transfer happens when the state of the system changes. So whatever the most stable state of your system is the one with the lowest potential energy. So your most stable state has the lowest potential energy. One way to think about this is if we had our stick of dynamite. So with our stick of dynamite, we know dynamite is extremely explosive. It has a lot of potential energy because it's extremely explosive. So the more explosive a compound is, the more potential energy it has. So lots of potential energy. Once you light the fuse and the fuse burns down, you get your explosion. Now all the molecules that made up the dynamite, when it had lots of potential energy, have now transformed into their elemental forms. which have a lot less potential energy. When it's in its elemental form, it has very low potential energy. Energy. So after the explosion, now those same atoms, very little energy, very little potential energy. Before that explosion, lots of potential energy. Which brings us to our first law of thermodynamics. Energy is neither created nor destroyed. So the energy is neither created nor destroyed. We can also say that the total energy of the universe is a constant. So the energy of the system plus the surroundings equals a constant. So our system plus our surroundings equals constant amount of energy, which means any energy transferred from a system must be transferred to the surroundings, or vice versa. It goes from the surroundings to the system. It can't go anywhere else. So that means our energy of our system equals the energy absorbed by the surroundings. So however much energy our system gives off, our surroundings have to absorb that energy. And it's exchanged as either heat or work. Ours, heat. So for our purposes in chemistry, heat. And so when we look at internal energy and the internal energy of our system, that's the sum of all the kinetic and potential energy. And so we call that capital E. And by definition, the change of internal energy, delta E, is the final energy of the system minus the initial energy. So delta E equals E final minus E initial. And if we think about the way that looks in chemistry, that would be the different states of our matter, the different states of our molecules. So when the energy is exchanged between the system and surroundings, it's either heat or work. So Q plus W. Delta E equals E final minus E initial. So in our case here, our initial state is at a higher energy level, because here's our internal energy. This is higher. When I take hydrogen gas and oxygen, they always combine together to give me water, which is a lower energy state. And so since water is a more stable configuration, this has lower potential energy than what we started here. So that means the energy of my system, the energy of these molecules, went from a higher energy state to a lower. That same amount of energy had to be absorbed by the surroundings. So it got transferred from the system, the molecules, to the surroundings. And it typically gets transferred as heat. So when you think about explosions, that's just a transfer of energy, just a very rapid transfer of energy. So when we think about this energy, it can go two ways. It can go from the system to the surroundings, or from the surroundings to the system. So if my initial state, E initial, is lower in energy than E final, the system has to absorb energy from its surroundings. So it's going to take in energy from the surroundings to go from the initial state to the final. And that's an endergonic process. If it does the opposite and it starts at a higher energy state and goes to a lower one, it releases the energy to the surroundings. And that's an exergonic process. So that's where E final is at a lower energy state than E initial. So it's going to give off the energy to the surroundings. And so when we're talking about, as I've been saying, when we're talking about energy in chemistry, we're talking about heat and heat energy. So remember, heat always flows from a warmer object to a cooler object. So if I take a beaker of hot water and I just let it sit there, it starts to cool down. If you take a cup of hot water and you just let it sit there, it starts to cool down. It'll cool down to room temperature. So it's releasing heat from that cup of water to the surroundings, to the air around it, or to the table it's sitting on. It's releasing the energy to that. If I start with a cup of ice water, so it starts close to 0 degrees Celsius, and I just leave it sitting out, it's going to warm to room temperature. So it's going to start to absorb heat from its surroundings to go from 0 degrees to room temperature. So that's an example of heat being absorbed from the surroundings into the system. So it's absorbing that energy. And a couple sign conventions when we're talking about heat. If I have a plus sign for heat, that means the system gains heat. So heat enters the system, which is endothermic. If I have a minus sign, then that means heat leaves the system. So the system loses heat. So heat's exiting the system, exothermic. So you can think of it endothermic, entering, exothermic, exiting. Same thing can happen with work. So if we think about work, if I start with a solid here and starts creating gas, that's going to create some pressure. Pressure will move the piston. And so with work, we have the same convention. If it's a plus sign, work is being done on the system. If it's a minus sign, work is being done by the system. So here we have work being done on the system. We have it being pushed. Here, the system is pushing the piston, so it's doing work. And when we look at work, that tends to be looking at pressure volume work. So if work equals that force times the change in distance, that can equal the pressure times the change of volume. If we think about gases, this is usually done with pistons. So if you think about your car engine and the pistons moving, they're doing work, and the chemical reaction happening in there is doing work on the piston. So when work is being done by the system, it's going to be a negative sign, right? So we have an expansion. So delta V equals V final minus V initial, which has to be greater than 0. So here, our piston moved up. So our V final is larger than our V initial. When work is being done on the system, V final is smaller than V initial. So if I take my larger cylinder here and I push that top down and make the volume smaller, I'm doing work on it. I'm forcing the volume to change to be smaller. And so looking at the sign conventions here, because we've been talking a lot about different letters and signs. First, if I have Q and it's positive, then heat flows into the system. So heat is absorbed into the system. That's endothermic. If Q is negative, heat flows out of the system. That's exothermic. If W, work is positive, work is done on the system. If W is negative, work is done by the system. If our delta E is positive, then the system has gained energy. So we went from a lower energy state to a higher energy state. Just like when we had that cup of ice water, we went from a lower energy state to a higher energy state. And then finally, if delta E is negative, the system lost energy. So that'd be that cup of hot water. It went from a higher energy state down to a lower one when it sat out for a long time. And so now you guys have seen heat, work, and energy. Should be able to look at a system and figure out which way the heat is flowing. whether work is being done on the system or by it. And then also tell me the total energy change. And so you should also be able to define what a system is and what the surroundings are.